All right, so a lot of good reading in section 104. This is the transport layer section. They're asking you to be able to explain the features and functionalities of protocols and technologies specific to the transport layer in this objective. This is where a lot of the meat is for understanding. This is where we start getting away from network engineering and start working our way up into application delivery. This is pretty much where the network engineers say, so I don't like to cross this line too often unless it's a firewall policy giving me a port assignment. Because usually, if in a network world, if you can ping it, my job here is now done. So we're getting into that transport layer where we need to understand about protocols at the transport layer, how things work. And the first point they want you to understand is to be able to compare and contrast the purpose functionality of MTU and MSS. So these two values control a lot of functionality within layer 3, layer 4. And MTU we've kind of already briefly discussed, and it is the maximum transmission unit. This is the maximum size of a packet allowed on a network in transport. It can be set to different values in a network because it can be administratively changed. By default, most systems are set to 1,500 bytes. MSS, on the other hand, is considered the maximum segment size. This is a parameter of the TCP protocol, not a layer 3 function, a layer 4 function of the OSI model that specifies the largest amount of data specified in octets that a computer or communications device can receive in a single TCP segment. So, how big of a chunk of data can my operating system process at a time? And this is based on different values and calculated by different values of the operating system. So every operating system will generally have a different value as their MSS. And in a three-way handshake and the TCP options that are negotiated between two systems as they communicate using TCP, they will decide what MSS size is going to get used. And so usually the smaller of the two MSS sizes between the two systems will end up being what's used. But let's say MSS size is large because we've got a really fast machine with a lot of RAM and a brand new fresh TCP stack. And it says, hey, I can process, like we said earlier, 4,464 bytes of data per segment. That's not going to fit in a single MTU regulated sized packet on the network. So we're going to have to cut it up into fragments at the network layer to transport it. And then we have to reassemble it coming back into that segment and hand that segment up to the TCP stack. And then they process segments at a time. And if a segment of data is missed, TCP will try to ask to have that segment resent. So this is back to those values that control the flow. And there's other pieces we'll talk about too in a minute. All right, so explain the purpose and functionality of TCP, right? The layer 4 protocol that is our transport layer protocol, primary transport layer protocol. It's not the only one. TCP is a reliable transport protocol, so it is probably the most commonly used transport layer protocol. It can, and it does have the ability to retransmit lost or missed segments of data through a very chatty process where the two systems are acknowledging that data was received, and we'll get into that in a minute. But TCP, even though it's a reliable protocol, it is definitely a chatty protocol, meaning it talks a lot between the two systems. It does add overhead to the overall data transmitted between two systems and onto your network. But it is reliable, right? It helps us transport data in a reliable way. We have other layer 4 transport protocols like UDP. UDP is not reliable or unreliable. One way, if you can't remember, if you don't deal with this that much. But UDP is another transport protocol that does not do the three-way handshake. It does not establish communication between the two systems and then send data. It basically just sends the data and hopes that it's received on the other end. Like we call that spray and pray, right? We're just going to send it out there and hope it gets to the other end. We won't know if it's received or not. There's no acknowledgments that come back. And so thus it is an unreliable protocol because we have no way to conclude whether it got to its destination or not. As the most interesting guy in the world would say, I don't always tell a UDP joke, but when I do, I have no way to tell whether you got it or not. Classic. They also want us to understand that all TCP and UDP, all transport layer protocols are based on communications between two systems or from a system to a system based on port numbers. We have ports assigned to every, port numbers assigned to every IP address on every system, and there are 65,535 unique ports available to any IP address to use for communication, and that's send and receive. You should be very familiar with the common ports, because sometimes we will ask questions based on port number or describe something based on its port number. Sometimes we describe it based on its protocol. And you should be able to correlate the two. If someone or a question asks, what port does HTTP run on, you should understand that that's port 80, right? If somebody asks, what port does SNMP run on, you should understand that it's 161, 162. And if it's SNMTP, Simple Mail Transport Protocol, that's going to be port 25. If it's FTP, it's port 21 and 20. But if it's active FTP, it's port 21 and an ephemeral high port that's negotiated between the two systems. So all these common port numbers you should be familiar with, just in case we describe them. When I ask you what port HTTP protocol runs on, you're going to say 80. But if I were to ask you what protocol runs on port 80, the answer is not necessarily HTTP. I can run any protocol over any port I want. So the standard protocol of HTTP as an RFC runs on port 80. But that doesn't mean that I couldn't put something else on port 80 as an administrator. So you should never assume, if someone tells you a port number, what protocol it is. But if somebody tells you what the protocol is, you can safely assume the port number. That's just one way to try to get through test questions. All right. So that's a kind of a cover of ports in general, and we may touch on some more stuff as we go through. Remember the 65,535. There's actually 65,536 ports, but 0 is reserved and represents all ports. So we don't use 0, we use the remaining 65,535 as available ports, right? They want you to understand the purpose and process of a reset. Reset is a function of TCP, and TCP being a reliable protocol, it's going to try to communicate between the two systems to acknowledge that data was sent, data was received, and that in that flow, if one of the two machines' systems are not behaving properly, they may leave it open-ended. They may not fin. They may not close. Right? They may not close the communication flow. And if that's the case, and the established system has an entry in its state table saying, I have a connection between me and another system on this port, but I haven't heard anything. As a timer counts down in TCP, it's going to trigger the system to say, hey, are you still there? If the system doesn't respond, he will not just close the connection and not tell anybody. He will use reset as a function to close that open connection, following that RFC standard, right? And so we have the ability for TCP to reap idle connections in its state table that it keeps to regain resources, because it takes memory to hold open those resources. So the purpose of a reset can be to clean up and recover resources on the operating system for idle or long-lived sessions that have gone idle, no responses coming back, things of that nature. They also want us to understand how retransmissions occur. So in TCP, like we said before, it's reliable and it has the ability to retransmit segments of data when they're missed. A typical default setting between two systems would look a little bit like the flow we have have here on this slide, where a laptop or a node on the wire makes a request to a server for, let's say, a web page. they're going to negotiate, going to do the three-way handshake, send, SYN-ACK, ACK. They're going to establish that three-way communication. Know they can have all their TCP options sets the way they need them to be, and that node is going to request data. It is a request response based HTTP in this case. Maybe if I'm going out across the web for a website, it would be a request response protocol at layer 7. So that laptop makes the request to the server for the website. Because, and we'll talk about this in just a minute, because that system is probably saying, the requesting system is saying, look, I can handle, because we've negotiated MSS size, I can handle 4,464 bytes per MSS segment, and the server agrees, and so they're both happy with that. And he may say, I have a window size of 4 that equals about 4 of those. So the server would know that it cannot send more than 4 segments at a time, or it would overrun the buffers. That's like that window size that the system sets. And so this is that flow control happening at the same time here. We'll talk about flow control in a minute. But the request gets made, and he sends across the first response to the first request in segments of data: segment 1, segment 2, segment 3, and segment 4. Because he knows he can't send 5 segments. The 5th segment can't be sent because he would overrun the flow control on the node. So he sends across the first 4 segments, and the first segment makes it, so the system would acknowledge 1, ACK 1. Segment 2 never gets received for whatever reasons. Let's just say it was at the fragmentation layer, it fragmented it up into 4 packets to transmit it across the wire, and it couldn't, not all 4 of them made it. It couldn't reassemble it on the node side, so it never handed that segment up to the TCP stack. But then segment 3 came in and was reassembled, and segment 4 came in and was reassembled, but they're not going to be processed yet because we have to process 2 before we can process 3 and 4. So when he receives 3, he will still acknowledge 1. That's the last one I've got that I've been able to process. And then when segment 4 comes in and he's got it, he's buffering, he's saying, hey, I'm still acknowledging 1. Well, the sending server now knows he's processed 1, right? And he needs to resend again so that segment 2 can be processed next. And so what will end up happening is he will, because he's gotten the acknowledgement on 1 and that was successful, he will send segment 2, 3, and 4. The reason he sends 3 and 4, even though 3 and 4 were actually received, he never got any kind of acknowledgement or any way to know that 3 and 4 were the ones that were received. Because there was a TCP option here that was not negotiated, and that was what we call selective ACK or SACK. So what ends up happening is segment 2, segment 3, and segment 4 get resent by the server instead of just 2, which is what was missed, because SACK not being enabled, he had no way to know whether or not those packets were received or acknowledged that they were received and being buffered, so he resends everything. So this next section here describes how if SACK was turned on, you could see that the flow would look a little different and a little shorter, thus less packets being resent. We still missed segment 2 for whatever network-based reasons that we couldn't get the segment back to the stack again. However, when 3 and 4 were received, instead of just ACKing 1 over and over again, he ACKs 1 because that is the last segment that he processed, but he also SACKs 3. And then as segment 4 comes in, he still ACKs 1 and he SACKs 3, 4. So now that tells that sending system that he is holding on and buffering segments 3 and 4, and that all I would need to resend to catch up is segment 2. So then he resends segment 2. That allows the receiving system to then process segment 2 because that's the next one in order, process segment 3 because it's coming out of his buffer, process 4 out of his buffer, and he'll acknowledge 4 going back, telling that sending system, hey, I've now gotten all 4 of those packets. Now, if there had been more packets to come, the server would have started resending packets as he acknowledged them, and that's due to the sliding window and the flow control, which we'll get to in just a second. So they also want you to understand and be able to describe all the various TCP options, and we've discussed a few of them already, like MSS and is SACK permitted or not permitted, time stamping, etc. And there's a lot of different TCP options. You should read up on them and be aware of them in case you're asked a question around a TCP option or what option would solve a problem. understand that TCP provides checksum value and checksum error correction for us as well. So if not only is it a reliable protocol, but it actually gives us the ability to know that the data being sent is reliable by doing the checksumming on it. So as TCP is sending, the TCP SAC sends a packet or the segment of data, he is wrapping that segment of data in a 96-bit pseudo header and calculating a checksum value against it. And thus the receiving system, when it gets that segment, it can wrap a 96-bit pseudo header around it as well, know that the checksum value matches, and be able to know for a fact that it doesn't need to have that data resent because it is the same value or the same data that the sending server has sent. And that's pretty reliable. It's just kind of interesting that it actually does that work for us. You should also understand how error correction works based on sequence numbers and error detection. Error detection could have come from a checksum error, or I've missed a sequence number, so I've processed segment 1 and I'd never received segment 2. I can't process segment 3 until 2 comes in. That will trigger that retransmit of data. This helps with error correction in the network, makes the protocol what it is today, which is reliable, right, compared to UDP, which just sends the data and doesn't care if it ever makes it to its final destination. We won't ask you about calculating sequence numbers because that's an algorithm-based function, and there's no way you could really do that in your head on a test. Just understand what they do is probably to the level you need to understand. They also want you to understand that the concept of flow control and how TCP uses flow control protocol-based function to keep the sending server from overrunning the receiving system with too much data too fast. So it's a sliding window flow control, which means if he says, look, I can handle up to 4 of these segments in memory at a time, the sending system will not send 5 at a time. It will send 4 at a time if that's what it's been told. And so as it gets an acknowledgement back on the first segment, it knows now it can send the 5th segment. And when it gets the acknowledgement on segment 2, it knows it can send segment 6 because it sent that initial 4 and it's waiting to get those acknowledgments back. So it's a sliding window for flow control. And that is how not only are we saying, hey, here's how much you can send me at a time, but now you can send me more. And that's what flow control is all about.